This is Larry Benko, W0QE, and this video is about SimSmith Generators. A generator in SimSmith produces an RF signal that is used in the circuit analysis, and there are at least 8 types available, and the user can create additional ones. I will show what the differences are for the different types, why they are or aren't useful, and finally when to use a specific generator. I planned to do this video a few weeks ago, but the new SimSmith version 16 had several small problems. In case you're unaware, version 16 is a rewrite of most of the code, allowing for new features. Consequently, it has been accompanied by several small bugs which were not found in the initial beta testing. For this video, I am using version 16.2B as in Bravo, which I've had for less than an hour, but appears to have fixed most everything that I reported. The SimSmith website still shows version 16.1AC for download, and I suspect the new version should be available very soon. Please check and download any new versions, especially until version 16 stabilizes. Alright, starting with version 16.2B as in Bravo, as I mentioned earlier, we'll do a file new, and we get a generator called useZ0. The useZ0 generator produces, without any parameters, it will take one parameter, which is a power level. Without any parameters, it produces 1 watt into an impedance here that matches Z sub naught. So if I have a 50 ohm impedance, it produces 1 watt into 50 ohms. If I have a 76 ohm impedance, it produces 1 watt into 76 ohms. You can think of it as being a generator that produces twice the voltage as is necessary when the load's correct, in series with a resistor that matches the load, which is why this symbol is shown this way. This is exactly how every quality signal generator made today works. Although the impedance does not have to be 50 ohms, a lot of times in audio range we use 600 ohms or we use different numbers. I think there are 75 ohm generators out there still too. But this is how a signal generator works. This model now means a couple things. It means that if you don't give the generator an impedance that matches Z naught, the generator will produce less power. And let's look at that. So we can take the load here and drag it. And if while I'm dragging the load, you look at this number right here, which is the power delivered into the load, you'll see that right here in the center I deliver a watt. Anywhere else I deliver less. I go out here further, it becomes less and less and less. Eventually, if I go all that near the edges of the Smith chart, it produces almost nothing. And that is what we typically refer to as mismatch loss. And mismatch loss, I've made the comment before, it's kind of like an opportunity that the generator had to produce a certain power but couldn't. That matches reality fairly well for a transmitter which does not have a microprocessor involved in it to artificially play games. But if you build just an RF generator, this RF generator will need to produce 7 volts and 141 milliamps to get 1 watt. Let's turn this into something that maybe is more typical. So let's say 100 watts. This generator now needs to produce, and this was the one parameter that this function has. I could have multiplied this by a number, I could have done other things, but I can also just put it in parentheses, it's a power. I could put a variable in here. Let's just do it. Such as, we'll call it power, it doesn't matter what we call it. It will create a new variable right there. We can put our power level right there, and we're back to 100 watts again. So, this generator needs to produce 70 volts at 1.4 amps. If I want to have an impedance that's out here, I need to produce more than 70 volts. If I have an impedance that's back here somewhere, I need to produce more than 1.4 amps. If my generator could do those things, then it could produce more in the middle here, and it wouldn't be a 100 watt generator anymore. It'd be maybe a 150 watt generator, 130 watt generator, something like that. So this represents what we see in a transmitter quite often. Now, considering that a lot of solid state amplifiers have issues with turns ratios and stuff that are integer numbers, you might get the generator might not be a 50 ohm output impedance. It might be a 45 ohm output impedance. And you can make, and I've made some tests on some different transmitters, doing something called a load pool test. That's load PULL, where basically I would give the generator various impedances, say on a 2-to-1 SWR circle, and I would look at them, or various impedances on a 1.5-to-1 SWR circle, and you would expect to see the same power delivered in all cases. And I can show that very quickly here. Piece of lossless transmission line. Let's make it long enough. Let's increase its length here. That's close enough, 32 feet. So now we'll go here and we will sweep the length of the transmission line. Look at this. And we see everywhere along the transmission line we have something's not right there. That's SWR. Where am I at here? Oh, it's a 100-watt generator. This is tough to do on the fly. Okay, we see that everywhere along here we see 88.9 watts. And it doesn't matter what the length of... Hang on. That's not a good... Let's go from 0 to 32 feet. Everywhere from 0 to 32 feet on this transmission line, the same power is produced into the load. And that means that the impedance we see right here, if we look at this impedance, it's all of these impedances right here. So that generator was centered at 50 ohms. A lot of solid-state transmitters will be centered a little bit less than 50 ohms because of turns ratios issues, and particularly the fact that we only have 13 volts to drive the amplifier stage. That's what that's just the way things are. But anyways, it's close to 50. So this represents a good use in general for almost all cases in SimSmith. Now, the next generator we can go to is called the X-Match generator. X-Match is a very interesting generator for a lot of reasons. And it produces, in this case, 100 watts into a load. Let's get rid of a piece of transmission line for a minute, and I'll just drag this around. Watch this when I drag it around. Doesn't matter what impedance I drag to, the generator produces 100 watts. Now, you might say that doesn't represent reality, and you're absolutely correct. It does not represent reality. But what it does represent is a way for me to divide the circuit up so I can look at just the match due to the circuit and avoid any kind of mismatch loss. This circuit has no mismatch loss, and that's its claim to fame. And we can continue on. The next generator is called an Output Z generator. Output Z is a generator which will produce... We set its output impedance. We can say its output impedance is, say, 50, C minus J20. So if I build a transmitter that was supposed to be a 100-watt transmitter, supposed to drive 50 ohms, but my output impedance was really this, I could use this as the model. And as I move the load around, this will no longer be the maximum power point. The maximum power point will occur when this is 50 plus J20, which would be the complex conjugate of that impedance, and it's 104 watts there. But it's pretty close. It's pretty close. Of course, if this is minus, say, 50 ohms, and this is plus 50 ohms here, then the difference is, I believe, 25. Yeah, it's 25% in power. But it lets you, again, it produces 1 watt into the impedance that is Z naught, with this output impedance, 50 minus J50 in this case. So it's a lesser used generator by far. I don't think I've ever used it for anything particular other than just to mess around. And let's get to the fourth power generator, which is the 4H. Well, I guess there are no more power generators. This is kind of a power generator. Let's skip it for a moment and go to the 4A transfer generator. This is a very special case of the use Z0 generator. It has no parameters that you can use with it. It produces all the time exactly 1 volt into an impedance that matches this. So in the case of the use Z0, where when I set this to be, say, 100 ohms, and I set this to be 100 ohms, I would produce whatever voltage necessary to get a watt here. this case, it produces always 1 volt. And that's used for making measurements with scattering parameters where you want the amplitude of the signal to be 1 volt. This generator is really not needed. You could easily just have used the UZ0 generator and multiplied it by the right amplitude to get 1 volt out. It's done for convenience. So it's not an absolute necessary generator, but that's, that's fine. It's there. There's nothing wrong with it. It just isn't something that we couldn't do another way. All right, now let's go to the last. There's 2 more generator types, fixed V and absolute V. And let's go to fixed V for a moment. And these parameters are no longer used, but until I set them to be equal to 0, they don't go away. So now they've gone away. Fixed V is a fixed voltage output. It's a fixed voltage source, 0 ohm impedance with it. It is calibrated to produce 100 watts, since I put 100 in the field here, into a load that matches Z0. Now, that's a little bit weird, but that's what it does. I don't find it terribly useful to want to put power into a fixed voltage generator, but it works that way. This is a much more useful generator to me. Now, again, we all have our opinions, and it does not have a parameter field that is power. It has a parameter field that is voltage. So let's leave the parameter field off for a moment. And in this case, this produces 1 volt into any load impedance there is. So let's just move around here, and we see, if you look right here at this point right there, we see it always stays as 1 volt. Doesn't matter. If I want to produce something like 5 volts, I can do this. The field is a voltage field now, and that produces 5 volts. Coincidentally, I'm capable of just doing this, putting 5 on the line. That's a 5 volt voltage generator too, produces 5 volts. Again, this does not have a whole lot of practicality for RF uses, but it's a very nice generator to be able to use in conjunction with, say, like a ruse block. You'd put a ruse block here, and you'd put all kinds of circuits in here, and you could learn a lot about AC circuits by having a fixed voltage generator, in some circuit. Because when you put a component now in a ruse block, remember you can right-click on it, and you can look at the voltage across it, the waveform, and you see the phase of it, the current magnitude, all that stuff. It's a really kind of a nice playground to learn about electronics. So you might say, well, you got voltage generators, why don't you have a current generator? And the answer is, well, I can have a current generator. SimSmith just didn't come with one installed, but I can easily make one. And all I need to do to make a current generator, I can make a fixed power current generator or just a current generator. And the easiest current generator to make is a 1 amp current generator, and all you have to do is type ZN. This is kind of cool. 1 amp current generator right there. Oops, let's get rid of this. 1 amp right there flowing. Now let me move the load impedance around. It's always 1 amp. So anyways, there's a number of generators. There are 2 more generators that are hiding from us. And those 2 generators that are hiding from us are in the ruse block, and they're not shown. However, if I go over to the preferences, and up here in the feature keys, they're available in the N block and the ruse block. And to make them show in the ruse block, I have to type VCVS, which is voltage controlled voltage source, or I can do voltage controlled current source. Click down on those, and now when I go back to my block, I have 2 more generators, and they can be used in the ruse block, and I'll demo those in just a few minutes. But that's the 8 different generators that I know of. There probably are more. Well, there are more because you can have user generated ones too, like the current source I did. But I made a little table here, and Here's a table. You can pause the video. Look at, these are the 6 that come with SimSmith. These were the 2 I was talking about making. This is the one I demonstrated. Didn't multiply it by a number, but I could have multiplied it by a number like 5, and it would have been a 5 amp current source. This is kind of if you're into algebra, this is the formula you could type in. You could type any of these formulas in, and you could achieve the same thing as this achieves. And I know this one, well, this one can be done a couple different ways for sure. This one was a little trickier to do, but they're fairly simple. But what you do is you write a couple formulas, and what you are trying to define is the voltage at the interface from the generator to the load based on all the things you know about. Zn is the impedance looking at that interface to the left. Z0 is Z0. If I wanted to have a UZ0 generator that was always a 50 ohm output impedance independent of Z0, I'd put a 50 right there, and I'd be done. And then a 50 right there for my, well, this one needs to stay as Z0 for the power, but I put a 50 right here, I believe. You can demonstrate that pretty easily. Anyways, I guess that's, enough of this. Let's talk about how we'd use them and the advantages of different generators. Let's take a very common example that somebody might want to do in SimSmith, and that is, let's have a load impedance that is not a one-to-one SWR with respect to the source impedance. And I don't know, I'm just making some numbers up here. All right, 10 minus J30. 10 minus J30 represents an SWR of 6.85 to 1. Similar SWRs could be seen on an 80-meter dipole that's being used at a different part of the band than it's cut for. If it was cut for CW portion, you want to use it at 3,900 plus kilohertz. You'd see SWRs like this. I'm going to put a piece of transmission line in here that's going to be 100 feet long, and it is the simplified model. And the reason I'm not using one of Dan McGuire's models is the fact that the K0, K1, K2 numbers don't have dB attached to it. They're embedded in those numbers. This is a 0.5 dB loss per 100 feet. I've got 100 feet loss of this. This has a matched loss. Now, again, it's important. It's a matched loss, not a current, not a loss with SWR, but a matched loss of a half a dB per 100 feet. I want to know how much loss does this piece of transmission line have in this circuit. If I use the UZ0 model here, I have a 100 watt generator. I am not putting 100 watts into this circuit. I'm only putting 56.5 watts into this circuit. The other 43.95 watts is mismatch loss. Maybe it makes more sense if I turn these into dB. Okay, so 100 watts, maybe it makes more sense to turn it into dB and go back to 1 watt. Okay, I have 1 watt, which is 0 dBW. I have minus 2.5 dB going into the transmission line. That means I have 2.5 dB of mismatch loss due to my generator not being matched to my load. Then my output power is minus 4 dBW. Well, does that mean my transmission line has 4 dB of loss? No. Does it mean it has 1.5 dB of loss? What is it? So this generator really is not a good generator. What I would have done in the past is I would have put a circuit in here. Whoops. I would have put a circuit in here. I would have matched this with Q that is extremely high components. And now you would see that I'm delivering 22 micro dB watts, which is virtually 0 dBW. I'm delivering the full power into here. And now I'm seeing on the output here a loss of minus 1.5 dBW. Remember, 0.5 dBW is the loss per 100 feet. So this piece of transmission line has an additional 1.006 dB of loss due to SWR. Hopefully that all makes sense. I can achieve exactly the same thing here by getting rid of this component and converting that to be the X match because it has a match in it. And there we are. So the X-match is extremely useful for things like this. I want to know the loss in this component, but I didn't want to be bothered by mismatch loss here. I was going to take care of that at some other point in time. So that's a very good use for the X-match generator. Continuing on, let's load a circuit. It's got too much stuff enabled here right now. What I have here is a pi filter. Nothing terribly special about it. And I have two load generator blocks and a real generator. So this generator drives this load, this generator drives this load, this generator drives this load, and I can have three outputs then that I can compare to each other. So I designed this filter, nothing special to it, and what it does is it has a little bit of peaking on it, and it's got roll off. It's a low pass filter, and I designed its complement, which is this circuit right here. So this is a low pass version of it. This is a high pass version of it. The high pass version of it should have the same characteristics as the other one does. Let's look at this one. We'll change this generator just for the moment to be and we'll look at it. Okay, you can see that the two curves are exactly on top of each other. So this circuit and this circuit perform exactly the same. Now, you might say, well, so what? They should perform the same way, and they do. But now let's look. Now we're going to look at these two. This circuit I'm going to keep up here for reference. This circuit I'm going to drive with a fixed voltage source. This circuit right here I'm going to change back to being a fixed voltage source. So let's go back here and we'll do clone the generator. So I got a fixed voltage source driving this capacitive input filter. I got a fixed voltage source driving this inductive input filter, and I've got this one for reference. It could be either one of the two circuits. It's driven from a UZ0. Now, we should have learned in previous videos that filters get their loss by mismatch loss. A filter that's good for, I have 1,000 watts I'm putting into these circuits. 1,000 watts would burn these components up if there was indeed, loss in the components. It's due to mismatch loss. So let's look at what happens with the other two circuits. They don't have anywhere near the same response. And when you design a filter, you design it for an input and an output impedance. And then the loss in that filter, with the exception of diplexing type filters, the loss in the filter is due to mismatch loss. And in the case of this filter, which has the capacitor here on the input, as the frequency goes up, the impedance drops. That means the generator sees a lower and lower and lower impedance. It's a lot of mismatch loss. So that's the kind of thing that you want to be cognizant of, the fact that if I have a source impedance that's very, very low or very, very high, one of these filters may be better for for your attenuation. It's easier to get attenuation with them. But nevertheless, the point I'm trying to make is this circuit, which has a capacitor input, and this circuit here, which has an inductor input, have different. Now they all have about the same response right there, but right here, all the filters look like 50 ohms. So 50 ohms doesn't matter whether this generator was designed to be a fixed voltage. It was going to produce 1,000 watts into a 50. It was going to produce 1,000 watts into a 50 ohm source, and that voltage that was produced would be the same voltage that would be used everywhere. So they all give the same performance here, but we look at the orange curve and we see it rolling off slower. It rolls off slower because the voltage source here just completely wipes this out. It's a 0 ohm source in parallel with this capacitor. The capacitor's out of the picture. So that component's gone. In the case of the in the case of this filter, this is still in series with the circuit, but the voltage source here is 0 ohm impedance. So the mismatch loss you get to a 0 ohm impedance is much greater than it is to a 50 ohm impedance. So we see that curve having even better performance. But in reality, the green curve is what we really want. So you can't just artificially use a voltage source or a current source in front of filters. You can also not use the X match in front of a filter. We could change this right here to X match, and we'd see X match is the worst match of the bunch. It didn't have a problem at low frequencies, but has a problem up here, and it just is driving 1,000 watts into this filter no matter what. I don't know what the impedance is it's using to drive it, but it's generating voltage and current. It's 1,000 watts. So here's a case where we definitely do not want to use the X match generator. Had you done this inadvertently, you'd be complaining about how your filter is, the performance of your filter is pretty bad. So again, that's another reason why you don't want to use the X match here. In my case, I use X match probably about 20% of the time for things like the coax example we did just a minute ago, and never for this type of stuff. And to finish this up, let me bring up one more circuit real quickly. And it shows the other type of generator. What do we got going on here? Oh, it was a note block I left there. Okay. It's a discrete Wilkinson combiner. Now, to do a power combiner, and we only have one generator, how do I do a power combiner which needs two generators? Well, I can get two generators by using these things called voltage-controlled voltage source or voltage-controlled current source. In this case, it's a voltage-controlled voltage source. I terminate the UZ0 generator that I had coming into my circuit with 50 ohms. These things have infinite output impedance, infinite input impedance, 0 ohm output impedance. They're differential in, differential out. They have common mode rejection ratio that's perfect. They're mathematical, so they're perfect. So this generator generates a voltage. This generator, which is connected to the same point as the first one, generates another voltage. Now, I've done this in such a manner that I have control over the phase and the magnitude of the second generator. The gain here can be a complex number, and that's how we set the amplitude and phase. If you use a real number here, it's just amplitude only. So I'm plotting start by plotting nothing here. We'll go back and we'll plot the power and the output. We see plus 3 dBW. This is a 1 watt source. Each one of these is a 1 watt source. They have a gain of 2 in series with a 50 ohm resistor, so it becomes the same W1. Well, let's look at W coming in. W0 coming in is a 10 volt peak signal, which is 7 volts RMS. W1 is right on top of it, almost, not exactly on top of it, and that's partially due to the fact that these components, which represent the lumped component Wilkinson combiner, are not perfect. They're pretty darn close. And we look at W2, and it's a little bit off. And again, it's the same kind of scheme. No, it's not off for that reason. It's off because I bumped this. Now they're off very little. Now, if we want to see how bad does a Wilkinson power combiner perform if the two phases are not equal. A Wilkinson power combiner is defined as a 0-degree phase combiner. It expects the two signals coming in to be in phase. Look what happens as I change the phase. I can see the red line here is the W2V, which is this signal right here. I'm changing the phase of it, and we can see the power coming down. So by the time I get to, say, 45 degrees, I've lost, I went from 3 dB to 2.3. I've lost 0.7 dB. And it would be the same on the other side, I'm sure. It'd be symmetrical on both sides. Same value again. So here's a case where we needed extra generators. We can do them inside the ruse block. This is incredibly powerful. I use this quite a bit. Not so much the current source one, but I use the voltage source one a lot more. I think people typically, myself included, gravitate to a voltage generator rather than a current generator. I had a discussion with everybody in a few videos about admittances versus impedances. And most of us think in terms of impedances more so than admittances. And the same thing is true of voltage source versus a current source. But SimSmith provides both. It doesn't clutter up this window if you don't have those two features on. If you do have these two feature keys enabled, then it does do that. If you turn these off and you had saved a file that still works, it just doesn't show you the symbol for them. But nevertheless, this has been an introduction into the different generator types. They have a lot of uses, and once you learn how to use them, they can make your analysis, your circuit, considerably simpler. And I made it through here without 16.2b showing me any problems. So that's a big plus for 16.2b. I'll report that to Ward. Thank you guys very much for watching the video. And hopefully this explains another piece of SimSmith. There's an awful lot of pieces to explain, and it's a very powerful program that can really improve your understanding of RF. Thanks again.